Good morning, everybody. How are you guys doing this morning? We are going to finish up our ideal gas law problems, and we are going to talk about gas stoichiometry today, and that's going to be the topic of our lab. Yes, we are going to have a lab that we're going to do from home, our only lab during this coronavirus pandemic, and so, hey, it works. Ideally, we would do all of our labs at school, but we're going to be doing this lab from home. So anyway, let's get started. If there's any questions, feel free to ask. I have not finished grading those. I've got a whole bunch of grading to do. I should hopefully finish grading your quizzes before next class. Wait, no, that might be tough. Next class is tomorrow. Maybe, who knows? Maybe I'll have them graded by tomorrow. Definitely by Friday. Anyway, so let's go ahead and jump into this. Does anybody have any questions on anything before we begin? I should say that we're almost done this particular unit, so we're going to be done this week, and actually this is the last topic of the unit, but we also have a lab, and we're going to expect to have the test next Tuesday, okay? So test next Tuesday on gases and all this kind of stuff. And we're going to be, wrapping up the year. So after this, we're going to talk a little bit about climate change, and then we're going to have one unit on nuclear chemistry, and that's it. So we're pretty much done for the year as this month, kind of comes to an end. All right, so let's jump into it. We have down here, we're going to just go into number 6, number 7, and then go do the whole back page, and then talk about the new stuff for today. All right. So what is the volume of 0.475 moles of a gas at standard temperature and pressure? Now, we could do this two different ways. We could simply say, okay, if we look back to number 5 from our previous homework and we said, okay, 1 mole of a gas at standard temperature and pressure has a volume of 22.4 liters, we could simply just do this and say, okay, well, that's going to be 0.475 moles, and so it's just 0.475 moles times this 22.4 liters per mole for an ideal gas and get your answer that way. Okay, so you could do it that way, but that's not going to work for a lot of different problems because you're not always going to be dealing with standard temperature and pressure. So the other way we could do it is to use this rearranged equation that we have, and that was volume is nRT over P, and plug in your numbers. For N, it's 0.475 moles. For R, 0.08206 liters atmospheres per mole Kelvin. Your temperature is at standard temperature and pressure. That's 0 degrees Celsius, which is 273 K. And then all divided by your pressure, which is just 1, right? Standard temperature and pressure is 1 atm. Okay, so either way, you should get the same answer. And so you can try them in your calculator. When did we do number 5? I'm pretty sure we did number 5 at the end of class yesterday. I think that I was going to end class and then somebody asked about it, and so then I just went over it. So I think that's what happened, but I'm not sure. Not yesterday, what am I saying? Yesterday we had the quiz. Friday, we went over it in class on Friday. Yeah. So, anyway, back over here so you could solve this problem either way. And if you're worried about number 5, it's solved exactly the same way as this. So you just you've got your pressure, your temperature, you've got your moles, and you're solving for volume. So you've got your PV equals nRT, rearrange to solve for volume, which is what we did here, plugging in the numbers. Okay. All right. So briefly, I can explain this part of it right here. Okay. So it's like, let me get another piece of paper. Here we go. Okay. So if you have any kind of ideal gas law problem, it's always going to be PV equals nRT. In both number 5 and number 6, we're solving for the volume. Right? And so because we're solving for the volume, you want to get volume all by itself on either side. All right, so what we do is we divide both sides of the equation by P, and that's going to make your P over P cancel out on the left side so that we now have an equation for volume. Volume is nRT over P. Okay, and so that, then you can just plug in for these. And for both number 5 and number 6, you've got standard temperature and pressure, which I tell you right here in the problem, the standard temperature and pressure of a gas is defined as 1 atm for the pressure and 0 degrees Celsius for the temperature. So we just plug in those numbers into this equation. N, for number 5, it says for 1 mole of a gas, right? So N is 1 mole. R is the same as always, 0.0206. T is 0 degrees Celsius plus 273, so T is 273. P is 1, and we said N is 1. So we just plugged in all those numbers right here. 1 mole, 0.08206, 273 over 1, and we got 22.4. Okay? So let's go ahead and do the math now for number 6. All right? Now you could do either one of these. We could take our number from number 5, multiply it by that. We're going to find that if we do that, 0.475 times 22.4, we'll get our answer, 10.64. And let's see if we get the same thing the other way. All right, so we use this rearranged equation, and we take our 0.475, multiply that by R. You probably should just go ahead and put R in your calculator if you can. I found that to be a little faster. So 0.475 R times 273, and then divide by 1, and well, you don't even need to put that in. So what's that? Look at that. It's exactly the same answer, right? 10.64. All right, you have some extra digits because our previous answer we did round this off, so it's not exactly 22.4. But in this case, we have only 3 significant figures, so it should be 10.6. 10.6 liters. 10.6 liters. Okay, guys, so any questions about 5 and 6 then? All right. Now, number 7, we are going to solve that. It's a similar type problem, and this one we could actually solve more than one different way too, right? So how many moles of gas are in 1 liter of a gas at standard temperature and pressure? Which, if 1 mole has 22.4 liters, it really should just be the inverse of that. And we're going to see that you can solve this more than one different way also. So let's just see, 1 divided by 22.4. All right, that's 0.0446. 0.0446 moles. But let's actually solve this the long way and kind of make some sense of it. Okay, and then we'll think, okay, why can I do that? Why can't I just take the inverse of this number? Because this is kind of there's an equality here, right? So we say 1 mole of a gas at standard temperature and pressure has a volume of 22.4 liters. And so if you have 1 liter, you would be 1 divided by 22.4 for that one. But let's actually solve it out. Let's go for the whole problem and see how that works. All right. So if we have, we're solving for moles. Okay. So we want to know moles. And we know the volume. It's 1 liter. And we know standard temperature and pressure. That's going to be your pressure is 1 atm and your temperature is 0 degrees Celsius or 273 Kelvin. Okay, so with this information, you can go ahead and solve for N. All right, and so solving for N, we need to rearrange the equation PV equals NRT. Solving for N, we're going to divide both sides of the equation by RT. That's going to get N all by itself over here. So N equals PV over RT. Okay, so let's plug in those numbers right now. Pressure is 1. Volume is also 1. R is 0.08206. And temperature is 273. So that's going to work out to be, interestingly enough, exactly the inverse of what we did for number 5, which is why my previous method did work. But we're going to do 1 times 1 is just 1, divided by, in the denominator, 0.08206 times 273, enter. And we get out 0.0446, which is exactly what we expected. We have apparently only 2 significant figures, which, okay, we'll just leave it at that, 0.045 moles. Okay, so that's the front page. Sorry, I didn't really give you guys enough space to do number 7 here, so scrunched it in a little bit. Hopefully that works for you guys. So that's the first page. We're going to go ahead and flip it over again. If you guys have any questions, feel free to stop me at any time. The back page is this one right here. And we are determining the pressure, in this case, number 8. We've got the pressure. So, P is what we're solving for, and 0.24 moles of gas right away, we can see, okay, that's going to be N. This is the temperature, right? But the temperature must always be in Kelvin. So right away, we're going to go ahead and convert this to Kelvin by adding 273. So this is 373 Kelvin, and this is our volume. Okay, so we have all 4 of those different variables. We're going to go ahead and solve for P. So we start with P, V equals nRT. If we're solving for P, we're going to divide both sides of the equation by V. That's going to get V over V. We're going to cancel out, and we are left with P equals nRT over V. Let's plug them in. N is 0.24 moles, R 0.08206, T is 373, and V is 7.75 liters. All right, that is going to give us 0.24, and I'm just going to use my R in my calculator. 0.24 R times 373 divided by 7.75, which is 0.94. Let's just round it off. Just going to be 0.95. 0.95. And what are the units? So pause here, and you guys need to make sure you're able to figure out the units. And so this is liters, this is degrees Celsius, that's moles. What's the pressure unit? And that's where we go back to looking at R. And it's so important to remember that R is not a unitless number. It's a number, it's a constant that has units. Liters, which means our volume is always in liters. Atmospheres, which means what? That means pressure is always in atmospheres. So our pressure, 0.95, must be 0.95 ATM. Okay, so number 9. Another problem, we are determining the volume. I think we got several of these volume type problems. So if it's volume, once again, we have PV equals nRT. Solving for volume, divide both sides of the equation by P. And P over P are going to cancel out, which leaves us with the volume is nRT over P. Let's put the numbers in. So we have 3.3 moles. So N is 3.3. R, same as always, 0.08206. Temperature is now 255, But we have to make sure we convert it into Kelvin. So it's going to be 255 plus 273, which is 528. All over a pressure of 0.895 atm. You need to make sure also that all the units are correct, right? Atm is the correct units, moles, Kelvin, and so we don't need to do any conversions other than that Kelvin conversion. So let's go ahead and do the math. So I'm going to use that 528 times 3.3 and then times R divided by 0.895, which gives me right around 160. So I think, yeah, for significant figures, we're just going to round that up to 160. So 160, and what are the units? 160 what? 160, well, the units, once again, go back to the units of R, 0.0206 liters. Liters is our volume unit, so this must be 160 liters. Okay? Number 10, determine the temperature. So this one's going to be a little bit different. Now we're going to determine the temperature, and that's going to be PV equals nRT. So this is, let's just identify, this is N, this is our pressure, this is our volume, and we want to determine the temperature of the gas in degrees Celsius. So if we're going to determine temperature, we need temperature all by itself. So what I'm going to do is divide both sides by what? By nR. That's going to get nR to cancel out on the right side. So divide both sides by nR. And so nR over nR cancel, and you're left with temperature equals PV over nR. Okay? So pressure is 1.25 atm, volume of 4.1 liters, N is 0.087 moles, and R 0.08206. Okay, so let's get that. 1.25 times 4.1 divided by 0.087 divided by 0.08206. And I'm getting 718 degrees. We're going to round that up to 718. 718 is what units? 718, of course, is going to be in Kelvin, because the temperature must always be in Kelvin. And anytime you do any of these kind of gas law problems, the temperature is going to be in Kelvin. But that's not what we want to actually solve for. We wanted to solve for, the question asks us in Celsius. So we're going to go ahead and subtract 273 in that case. And that's going to give us 445. So 445 degrees Celsius. All right, guys, pause there. Any questions? Are we good so far? All right, let's keep rolling. Number 11. You got a certain gas, 9 degrees Celsius. Of course, once again, we're going to always convert these temperatures to Kelvin, right? And so what's that going to be? So 90 and 273, that's going to be 363 Kelvin. That's our temperature. And we have a pressure of 1.25 atm and a volume of 0.65 liters. How many moles? So now we got to solve for something different, right? So we're solving for N, which means we're going to take that equation and rearrange to solve for N. So PV equals nRT, solving for N. So we want to get both sides we want to get the n all by itself, so we're going to divide both sides by RT. That's going to have RT over RT are going to cancel, and we'll be left with N equals PV over RT. And so pressure is 1.25 atm. Volume is 0.065 liters. R 0.08206 liters atmospheres per mole Kelvin. And temperature is 363 Kelvin. All right. Plug in the numbers, and we'll get the value of R. 1.25 times 0.065, right, divided by R, divided by 363, gets us 0.0027. And I think we have only 2 sig figs, so that's going to be good. 0.0027. 0.0027. And of course, for moles, the units are moles. 0.0027 moles. And then that's that. All right, last problem, guys. Let's go ahead and look at the last problem here. Oh, and the last problem isn't really so much a problem that's terribly important for you guys. I just wanted to go over this a little bit and just show you guys how this can work. But just in all honesty, this is not going to be too important for you guys, okay? Because, yeah, let me just show you how this works. So Boyle's law and Charles' law are all related to the ideal gas law. So at the very, very beginning, when we talked about the ideal gas law, we kind of looked at the gas laws and combined them together to make the ideal gas law. But let's just go ahead and do this. So for Boyle's law, we are looking at pressure. So what are our variables? Our variables are pressure and volume. And in Boyle's law, you have a lot of constants, right? And that's important to recognize. So your constants are what? These are our variables up here. Variables. Right, so we were kind of wondering, okay, how are P and V related? So our constants are what? Your constants are going to be temperature is held constant for Boyle's law, and the amount of gas is held constant for Boyle's law. So when you look at the equation, PV equals nRT, well, N is a constant, R is always a constant, and T is a constant for this situation. So you're holding temperature and moles constant. Okay, so PV, and you could just call these whatever. So PV equals, so some constant times R is another constant, T is another constant, and so K1 times K2 times K3, so any constant times another constant is always just going to be a constant, so you could just call this K4 or whatever. So PV is a constant, and that literally is, so PV is a constant, that's what Boyle's law is. And that's how you're able to say, well, because this product is a constant, therefore we can also say P1V1 equals P2V2, because pressure times volume is always going to equal pressure times volume as long as N and T are constants. All right, so that's kind of the way you would go about it for Boyle's law. Charles' law, exactly the same thing. So Charles' law, you just look at, okay, what are my variables? Your variables are going to be V and T, and now your constants are going to be pressure and N. And so you have PV equals nRT. And now we can go ahead and we're going to put your variables on the same side. So V and T need to be on the same side. All right, so you can just divide both sides by P. That's going to get you V equals nRT over P. And then we wanted to divide both sides by T, so we could get T on the other side. So we get our variables all on the same side. So that's going to get us V over T equals nR over P. Well, we know N is a constant, R is a constant, P is a constant in this case, right? So we're holding pressure constant and we're holding the number of moles constant. So we can say, okay, V over T, constant times a constant times a constant is simply some other constant. And so V over T is a constant. And once again, that's what Charles' law looks like, right? Charles' law looks like V over T is a constant or T over V is a constant. So therefore, right, V1 over T1 equals V2 over T2. Because this ratio is a constant, you can use this kind of equation. So that's it. That's really not that important. You're not going to have something like this on the test. You will have any of these kinds of problems that you had in this homework. Any of the other problems in the test, or any of the other problems in the homework can most certainly be test problems. Now, it's time to go ahead and jump into the new stuff, which is the last thing that we're going to do for this unit, and that is gas stoichiometry. And this is a beautiful, beautiful lesson, and it's going to be a beautiful, beautiful lab because it's going to bring together some of the various things that we've learned. It's going to bring together chemical reactions and stoichiometry and now gases and even a little bit of solutions all here together. So I know it can be a little bit overwhelming, but it's also beautiful because being able to solve this shows that we have learned things as we've progressed through the year. Okay, so this is, probably the most important thing that we are doing this particular chapter. All right, so let's do it. Gas stoichiometry, right? And because all the stuff in chemistry is really geared toward chemical reactions. That's, you can ask people different things, but in all honesty, the most important thing in chemistry is your chemical reactions and understanding how they work and getting them to work for you and all that kind of stuff. So I'm going to go through 1 and 2, and you really only have a few homework problems. So I know it's a little, these problems can be difficult, but you only have really 2 of them. Okay, so this is one sample thing that I'm going to go through, and then all you have to do is, 3 and 4, 3 is just balancing, and then 4 is the stoichiometry problem. And then on the back side, you've got simply just, one problem, right? That's it. So not a lot of problems, so spend the time to understand them, all right? And don't zoom through them because you don't have a lot of homework. You just have, some challenging homework. All right, so here we go. Magnesium. It's added to a solution of hydrochloric acid, and we remember, hopefully, that hydrochloric acid is HCl, okay? And they react to form hydrogen gas. So a metal plus an acid is going to typically, but not always, typically make hydrogen gas and aqueous magnesium chloride. Magnesium chloride, well, what in the world is the formula for magnesium chloride? Well, hopefully we remember that magnesium being in the second column in the periodic table, let's bring it up here. Here's magnesium right here. Second column in the periodic table. So when magnesium is in an ionic compound, it has a 2+ charge. And chloride is in the next to last column, which means it has a -1 charge. Remember, last column is 0. Here's -1, -2, -3 for nitrogen. Okay, so Cl-. Now that we know the charges, we can figure out the formula of magnesium chloride very easily. The 2 numbers, that 2 and the 1, they just flip, and it becomes MgCl2. Okay, so magnesium reacts with hydrochloric acid to make hydrogen gas, and this 2, where in the world did this 2 come from? Hydrogen is diatomic, right? Because hydrogen is diatomic, we know that 2 is going there. And diatomic things are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, right? So this is diatomic, so H2, and we're making magnesium chloride, which we figured out has this formula right here, MgCl2. So what kind of reaction is this? Do you guys remember? Anytime you've got a single element, this is actually not an acid-base reaction because there's no base. There's just an acid and a metal. Anytime we have a single metal, a single element, and a compound, that makes a single element in a compound, that's going to be what? SR. Do you guys remember? Hopefully. Single replacement. Single replacement reaction because, right, we got a single element plus a compound to make a single element plus a compound. The magnesium comes in, kicks out hydrogen, and hydrogen is now all by itself. So that's a single replacement reaction. And we, of course, need to balance it. It's not balanced because we have 2 hydrogens here and we have only 1 there. So we're going to put a 2 in front of HCl. That gets us 2 chlorines here. And look, we have 2 chlorines there. 1 magnesium, 1 magnesium. So this 2 balanced everything. So we're all balanced. Okay? So now that we're balanced, we can go ahead and solve the real big part of the problem. And that is this. Suppose you wanted to fill, and this is very applicable to the lab that we're going to be doing, right? We're going to fill, in the lab, we're going to fill a balloon with a gas. It's not going to be hydrogen, it's going to be something else. But suppose you wanted to fill a 2-liter balloon with hydrogen. How much magnesium and hydrochloric acid would you need? Okay, and we're going to assume this. All right, so this is kind of like a problem where you might be thinking, where in the world do I even start to answer this? Well, thankfully, I'm going to tell you. You're going to start with trying to figure out N. Why? Because we know the temperature, we know the pressure, and we know the volume that we want. And once you figure out N, then you can go back and calculate the amounts of magnesium and HCl that you need using stoichiometry. Okay? So let's first calculate N. Right? So we have PV equals nRT. So therefore, to get N all by itself, divide both sides by RT. RT over RT cancel. So N equals PV over RT. N is going to be your pressure, which is, that's 1. That's not late, or that's 1 ATM. Volume is 2 liters. R 0.08206. And temperature, we said, is 25 degrees Celsius. 25, we need to convert that into Kelvin. So 25 plus 273 is 298. So let's do that. We're going to calculate N first. Sometimes you might do this process in reverse and first calculate, the moles and then use that to calculate, let's say, the volume of gas. Okay, in this case, we're going to be starting with the volume of gas and calculating N. And I think, honestly, that's what we do for most of these here. Yeah, I think that's what we do for all of these. So all of these are kind of the same process. So let's do it. First, calculate N moles of gas. So it's going to be 1 times 2, which is simply 2 on the top, divided by, in parentheses, 0.08206 times 298. Enter. And we're going to get 0.0818. 0.0818 moles. And what I'm going to do is I'm going to keep that number in my calculator. Maybe I'm going to store that as X, because that's the number of moles of gas that I have, right? The number of moles of gas that I have is this. So that's important, but that's not my final answer. Okay? What topic are we doing next time? For after we're done with gases, I'm going to do nuclear here. We're going to do nuclear. But before we do nuclear, we will do climate change. So a little bit on climate change. Okay. So this is moles of gas. All right. Now that we know the moles of gas, what we're going to do is we are going to use that number to figure out how much magnesium and how much hydrochloric acid that we have. Let's start with magnesium. Okay. So we have 0.0818 moles of H2. And why is it H2? Because that's the only gas that we have. All right. The only gas we have is H2, so this is moles of H2. Right? We got that from the volume. Now we're going to use stoichiometry to first convert that to magnesium. Okay? And that's simply because we have one hydrogen here and one magnesium here. All you do is say, okay, one H2 on the bottom, because we're starting with H2, is going to make one, we're going to use 1 mg. So no math there, just times 1 over 1. Finally, we want to convert this because we don't just want to know moles of magnesium, but in real life, you need to weigh out the magnesium somehow. So we want to get the mass of magnesium. So what we're going to do is we're going to look at the periodic table, get the mass of magnesium, which is 24.305. Oops, I don't know if you guys can see that. 24.305, that's the molar mass of magnesium. 24.305 grams per mole, which is going to be, and let me just make this clear here. So that's going to be this number, 0.0818, which we have stored in our calculator, times 1, which is the same thing, times this 24.305, and then boom, 1.99 grams. Okay, 1.99 grams of magnesium. All right, that's the amount of magnesium that you need. But wait, there's more. Because you have two reactants, you have magnesium and hydrochloric acid, we need to know the amount of each of them. So we're going to go one more step, and that's going to be 0.0818 moles of H2. And now we're going to say, okay, how many moles of HCl do we need? Well, we have, for every one H2 from the balanced reaction, we actually need 2 HCl's. That's going to give us moles of HCl. And last of all, we want to convert that into a volume, liters. So our conversion factor rate is this number right here, this moles per liter. So we have 0.5 moles per liter hydrochloric acid. And so that's going to be 0.5 moles per liter. The moles is going on here to cancel out the moles that we started off with, and the liters is because we want to convert it into a volume, something that we can use in the lab. Remember, we're all the time thinking about how can we do this in the lab. So we're going to start with X again, this 0.0818 times 2 divided by 0.5, which is in a sense just multiplying the whole thing by 4. And that's going to give us 0.327. 0.327 liters. Okay? If you wanted to, you could go ahead and convert that to milliliters and say, okay, that's 327 milliliters, but you don't have to do that. You can just leave it as 0.327 liters. All right, that's it. I know this is a challenging problem, perhaps one of the most challenging problems that we've ever had, but I know you guys can do this, okay? Just follow my example and do it for these other two problems, and you'll be fine. 3 and 4 are going to be a little bit easier because you have only one reactant in that case, but the backside is going to be very, very similar to this one where you have 2 reactants and you have to calculate them both, okay? So guys, we are going to, so this is homework, this is due tomorrow. We're going to go over the answers tomorrow, so make sure you do this for homework. We're going to go over the answers tomorrow, and then you will have a lab which works exactly the same way. Okay, you're not going to use hydrochloric acid, you use vinegar instead in your lab, and you're not going to use magnesium, you're going to use baking soda in your lab, but it's the same exact kind of math involved for the lab. Okay? So, do we have to balance them? Yes. This definitely needs to be balanced. Look at that. There's 3 ends there and only 2 ends there. And on the back side, mine, I didn't print it double-sided here. And on the back side, same thing. We've got 1 chlorine, 2 chlorines there, 1 hydrogen, 2 hydrogens there. And so this one's going to balance in a very, very similar way. This one's like almost exactly the same kind of problem as the sample problem that I just went over. Okay? And then numbers 3 and 4 are a little bit easier because there's only 1 reactant. And this is a real problem, right? This whole reaction here is used in real car airbags. So we're going to go ahead and end there. Sorry, I think we went a little bit long, but wanted to make sure I get that finished. And I hope you guys have a wonderful rest of the day. Does anybody have any questions? All right. If there are no questions, I'm going to go ahead and sign out. So see you guys. Have a great rest of your day.